Hello Year 10 and welcome to our last chemistry lesson this term, because after this we will be preparing for a test. So what I'd like you to do now is 1, calm down, 2, do the do it now task. I want you to define the following words as a really good revision. Don't forget, if you're doing higher tier, oxidation and reduction may need an extra definition. So just in case you can't read it, your words are anode, anion, cathode, cation, oxidation and reduction. So pause the video and define those now. Thank you. Hi Year 10. So hopefully you have defined the following. Let's go through the answers. An anode is a positive electrode. An anion is a negative ion, so usually a non-metal, so oxide, chloride, they usually end with "ide." There's a bit of a hint. A cathode is a negative electrode, and a cation is the cation is the positive ion. So the anion is attracted to the anode, and the cation is attracted to the cathode. So just remember the first bits are attracted to each other. And metals and hydrogen are usually positive ions. Oxidation means adding oxygen, or for higher tier, it's loss of electrons. And reduction is when you remove oxygen, and for higher tier, it's a gain of electrons as well. So what we want to look at today is reversible reactions, dynamic equilibria, and the Haber process. You might be like, oh, that's so much, but it's really not, because they all link in really well together. So first of all, reversible reactions. Now, we are really used to seeing a reaction looking like this. So if we just take a look, we have got, for example, nitrogen and hydrogen make ammonia. Okay, so nitrogen and hydrogen make ammonia. I've balanced that for you because I know we've done this one several times in lessons, but that's not always the case. So what we also get is ammonia can break apart to make nitrogen and hydrogen. So instead of writing out the equation twice, this is what we do. It's really clever. So I'm just going to switch pen colour. Nitrogen plus hydrogen, and we're going to get ammonia at the end. But watch this, because you're going to have to draw this symbol. It's one of my favourites. Yes, it goes this way, but watch this. It also goes that way. It's a reversible reaction. It can go one way or the other. And I'm not going to sing. I'm really not going to sing. Sorry, I've got to stop myself. So it can go one way or the other. And what happens is we can use this to make what we want and have a play around with it. A lot of this stuff is going to be higher tier. So it's called a dynamic equilibrium, okay? Because you've always got nitrogen and hydrogen making ammonia, and you've always got ammonia breaking down into nitrogen and hydrogen. It doesn't sit still. It doesn't say, you know what, 70% of us are going to be this and 30% of us that. And so once we've made 30% of us being ammonia, we're just going to stop. No, you've always got something going this way, something going that way. Ooh. It's like, I'm just trying to think of this. It's like if you watch the escalators or the travelators in a shopping centre or a supermarket, and there's always people going upstairs with the trolley and always people going down the stairs. And you generally have the same amount of people in the bottom of the store as you have in the top of the store or the shopping centre or whatever, but people are moving between the two layers all the time. And that's exactly what's happening here. Okay, so now we need to look at the Haber process. The Haber process, named after Fritz Haber, is where you take nitrogen from the air, and the air's about 80% nitrogen, just a bit less, and you take hydrogen from natural gas, so that's things like methane as well that come out from there. You separate out the hydrogen, you run it with a high temperature and pressure to make it go a bit faster, and you run it over an ion catalyst and you make ammonia. Yeah? So far, so good. But the problem is we've just seen is that making ammonia from nitrogen and hydrogen is dynamic. You're going to be making it and you're going to be breaking it down, making it and breaking it down all the time. It's a dynamic equilibrium. It's always on the move. Hence why I am moving, to show you that this equilibrium is constantly shifting and moving. It doesn't ever stay still. That's what dynamic means. If you watch the 1960s Batman series with Adam West, please do, it's amazing. Batman and Robin are called the dynamic duo because they never ever stand still. They're always biff and kapowing and zapping all the baddies. They're always moving, they're dynamic, same as this equilibrium. It's reversible and it's dynamic, it's moving backwards and forwards. So what can we do if it's breaking down at the same time? So what happens is, once you've passed the nitrogen and hydrogen over an ion catalyst with a lot of pressure, so you're pushing it all, and it's quite hot to make the reaction happen more quickly. Actually, you do need to know this, so I'm going to write this down as well, which is it's at 450 degrees C, so it's quite hot. So 450 degrees C, and it's at 200 atmospheres of pressure. All right, so let's just look at that. 200 atmospheres of pressure. So you think you're feeling a little bit of air pressure pushing down on you at the moment? No, this is 200 atmospheres of pressure, and that's really pushing down on the ammonia. And I'm not going to start singing either again. I do love under pressure, but no. So it's hot, it's under pressure, it's pushing down on me. No, and you put it over an ion catalyst, and you get your nitrogen and hydrogen all reacting and your ammonia. The problem is the ammonia is then turning back into nitrogen and hydrogen. So what do? Well, it's nice and hot, so everything is a gas at the moment and just moving around and breaking up and remaking itself. So what happens after they've made it is they cool it down. So once you've done your reaction with your catalyst, you cool everything right down, and your ammonia is a bigger molecule than your nitrogen or your hydrogen. And it also does this thing called hydrogen bonding, which we're not going to worry about too much just yet. And so all of this turns into a liquid, and instead of zooming around everywhere because it's a gas, it's a liquid, and it condenses down at the bottom of the reactor. And there's a nice little, I'm going to just call it a pipe and a tap because you'll understand that. And you can just literally run all this liquid ammonia off. Ammonia, remember, is what gives your smell. So you really don't want to be smelling this stuff coming out of the little tap at the end of the reactor. You're still left with a load of gas. And this is the really clever bit, because instead of saying, well, this is all wasted, let's just shove it out into the atmosphere. No, all the gas is still moving around in the table and not getting lost like that hydrogen did. And there's a little pipe that takes it all the way back to the start of the reaction so that the hydrogen and nitrogen can react together again and make ammonia, so they are able to recycle the gases to make more ammonia, and that makes the yield higher. It makes it a more effective process. Okay, are there any questions so far? Does that all make sense? Okay, if there are any questions, email me, because that's it for the standard paper. That's all you need to know. Okay, that a reversible reaction can go either way. It's a dynamic equilibrium. It's moving the whole time. Your molecules don't just get there and sit sorted. They're moving backwards and forwards. And you need to know the Haber process: nitrogen from air, hydrogen from natural gas, ion catalyst, 450 degrees C, 200 atmosphere pressure, makes ammonia, which is taken off as a liquid. Higher tier, you need a little bit more information than that. So why the high pressure? If you'll just excuse me a second to get my hydrogen back. So I've got my hydrogen back now. Look at it like this. Here on our reactant side, we have got 4 molecules. Yep, 4 molecules. On our product side, down here, we've got 2 molecules. If I'm going to put the pressure on, if I'm going to squeeze these up as tight as they can get and squeeze these up, what do you think is going to be better? 4 molecules or 2 molecules? Which is going to be easier to squish, 4 things or 2 things? The 2 things are going to squish up and take up so much less space than the 4 things. Okay, because I can't actually get this close in real life. There's always a bit of a distance. So the high pressure is going to push the dynamic equilibrium over towards the area where there's fewer molecules, so over towards making ammonia. Okay, unfortunately, this reaction is exothermic, so it gives off heat. The reaction going this way to make our gases is endothermic. So if we do it at heat, we're actually encouraging this stuff to be made because we want to keep our temperature roughly constant. If we did it at a cold temperature though, we wouldn't have the energy to make the reaction happen. And although it would happen really slowly, so it wouldn't be worthwhile doing. So it's actually a compromise. This high temperature is nowhere near as high as it could be. They could do it at 900 degrees C if they wanted. It's to make it go quickly with a huge amount of pressure to try and push it towards making ammonia. But the temperature's there just to make the reaction happen quickly. Because if we didn't have the pressure, we wouldn't make any ammonia at all due to the temperature. Okay, so we can affect the dynamic equilibrium. This is the really important bit. We can affect our dynamic equilibrium by changing the conditions. We put it under more atmospheres. We're going to push it more towards making, more pressure, not more atmospheres. We're going to push it more towards making the ammonia. But it takes a lot of energy, costs a lot of money to put that amount of pressure into a system. And the more pressure you put in, the bigger the system has to be and the more thicker the walls have to be to withstand that pressure. And so it costs more to set up. So this way it's cheaper to do 200 atmospheres pressure than 300. You'd get a better yield with 300, but it would cost a lot more. So we've got to think about money as well. That's pretty much what you have to know. Are there any questions? If you do have any, email me. That's what you have to know for reversible reactions, dynamic equilibrium and Haber process. Hopefully I've made it sound really easy. So check out the worksheet I've got for you on the Haber process. It gives you a nice picture of what's going on in the process, a lot more than I have done. If you have your worksheet and watch the video, you should be able to spot what's going on where. So you've got your gases in at the top, nitrogen and hydrogen, over the iron catalyst to make the ammonia, and the ammonia comes off at the bottom and the gases are recycled. Hopefully it will all make sense with the worksheet. Any questions, please do email me. That's what I'm here for. Yeah, good luck with that. And don't forget, we need to do all of those lovely revision things, that memory tricks that we were talking about on Monday for you to really succeed in the test. So take care and I will see you soon. Bye.